like to share. I would like to share with you a little bit of experiences we have done along the way while solving inverse problems in combination with machine learning methods. And I would say that quite a lot of work in our group at the moment is maybe a bit more on the forward end of things, but this talk will mostly focus on inverse problem part of inverse problem. Inverse problems contain forward operators, and these forward operators act on coefficients that we want to reconstruct. So there is a tight relation between a forward and inverse problem, but here we will focus on the inversion. Okay, so let me very briefly introduce you to a problem that I spent quite a lot of time over the last couple of years with, and you may not have heard about this if you are no inverse problem person. It's called photoacoustic tomography. What we are particularly excited about this in this modality about is that it combines a very relevant biological contrast mechanism, that is optical contrast with a resolution of ultrasound. So the idea is that we are illuminating the tissue with a pulse of near infrared light. So this light will diffusively propagate through tissue, so we are not transparent, basically, to waves, not even near infrared. So it will be diffusively propagating through the tissue, and this process will result in something that we call the fluence, which is essentially the distribution of the light in a volume. And now this is going to be absorbed by the tissue in correspondence with the tissue coefficient, such as absorption coefficient in that case. And so upon this absorption, the tissue will heat up and it will expand, and this it will cause a pressure rise, and this pressure will be released in the form of an acoustic wave. And this acoustic wave we are going to measure on the sensor on the boundary of our domain. So this process is called photoacoustic process, the process of conversion of the light into the sound. And this is the same process that makes the thunder. We have the lightning that strikes, and then we hear the sound of the thunder. So this is exactly the same effects that this methodology is utilizing here. So we are going to be recording this acoustic wave, and in particular, we're going to be recording a pressure time series as the wave passes through the detector. So we have been working on this problem in collaboration with our colleagues in photoacoustic imaging group, and they have been developing a corresponding scanners. We have went through many iterations of ideas how we can speed these things up. And so this is kind of the latest flagship scanner that essentially combines the logic to measure the pressure time series as it comes through the detector in a very efficient way. So it's interesting. It's interesting methodology. So this is an interferometer, and this is a light. So it is optically interrogated acoustic sensor, and this is being done in parallel with multiple focus beams and recorded by the electronics. So it's quite an achievement on their side to put together this as a device. Okay, so now mathematically we can look at this problem as a forward problem, and we want to of course invert the data. So we also would like to have some sort of inversion procedure. So, but first, the forward. What is the forward model? The forward model is the wave equation, and it is actually an initial value problem for the time domain wave equation. And we have initial data that corresponds to the initial pressure, which is the initial pressure that I talked about, that is a result of the heating of the tissue. Because this is a second order equation, so we have the second initial condition, and this is a modeling assumption that this can be set to 0. This corresponds to the time scale of the heating up and the propagation being vastly different. So we can assume that the change is instantaneous upon the heating up of the tissue. So we have this wave equation, and in photoacoustic imaging, we usually assume the speed of sound to be constant. And we assume it to be known. It doesn't mean that it is always a perfect assumption, but it works out fine enough for most of the applications. If there is no way of measuring the speed of sound, this is anyway the best assumption. So it is going to be a wave equation with constant speed of sound. And our data corresponds to, when we want to tap into the data from the forward model, we will solve the wave equation, and we will evaluate the solution over time on the detector and record it. So this is going to be our forward model, the data corresponding to the forward model. So it turns out that the adjoint to this forward model is another wave equation with the initial value now set to 0, however, with a time-dependent source at the boundary, and the time-dependent source is exactly the pressure time series data plugged at the locations of the sensors, but in a reverse order. And now we can solve this source wave equation, and we can evaluate the solution at the time t or across the whole domain, and we are going to obtain the application of the adjoint operator. So we also have something that we call a time reversal in photoacoustics, on generally more in wave propagation problems. But essentially what it is a way to refocus the wave, or to solve a boundary value problem with the data now in the time, again in the time reverse order, playing the role of boundary conditions. So again, we have initial value of 0, and then we have this data that are now the boundary control, if you wish. So again, we will solve this this problem for up to time t, and we evaluate the solution over that whole domain, and we are going to obtain the refocused wave. So this is an inverse of the wave equation under rather clinical conditions of the sufficient smoothness, well-behaved speeds of sound, 3 dimensions, and measurements all around, sufficiently around the object that we are looking at. So in practice, in particular in this half-space geometry that we are looking at, which we are looking, it is impossible to fulfill those assumptions. So we are somehow faced with some kind of inexact inverse, maybe approximate inverse, if we look at this operator. Okay, so given that we will have most of the cases we are going to have incomplete data, so this inverse application of this analytical inverse, or in this case numerical evaluation of that inverse operator, is not going to provide us with a very good reconstruction. So we are going to get something, but it's not going to be a high quality reconstruction. So in different regimes will result in different sort of artifacts that we can see, but in general, there is going to be some deprecation of the quality. So people are usually looking at, in such situations, at posing the problem in variational form and solve it as an optimization of the data fit versus some sort of prior knowledge that we assume about the object that we are reconstructing. So this can be thought of, in the Bayesian framework. This can be thought of from the inverse problems perspective. We usually think of this as a regularization, and we end up with this sort of variational formulation that trades off the data fit against the regularization. Functional, of course, in this model we have the assumption that we have some sort of noise in our measurements, and this data fitting functional here should go in tandem with what sort of noise we are considering, be it Gaussian noise, for the to be Poisson noise, KL diversions, and stuff like that. And on the other hand, here we have this regularization functional. And because we are in the business of reconstructing images, so we usually very much care about the singularities being preserved. So this means that using some smooth functional here is usually not a good option for imaging. While the data functional is frequently smooth and differentiable and so on, so that's not going necessarily to be the case for the regularization functional. And the kind of if you want to, so therefore, when you want to solve this problem, we are sort of in a, if we assume this functional to be convex, that we usually do, in order to keep some theory from inverse problems going, we are going to have to deal with the fact that it is not the differentiable functional. So the simplest method that we could come up for the solution of this sort of formulation with the non-smooth regularization functional is such a proximal gradient scheme, where we take the gradient step with respect to the differentiable part, and then we take the proximal step with respect to the non-smooth regularization functional. So this proximal operator here amounts to solution of the following denoising problem which balances the proximity to the image Y and minimization of the regularization functional R. So this is kind of very classical method by now, coming from the convex optimization. So we typically will have, as I mentioned before, for example, for the Gaussian noise, we will have the L2 square data fitting functional, and the simplest regularization term we could come up with would be to penalize the to assume that the solution should be non-negative. So basically to penalize the negative value of the solution here, very brutally penalizing them by the characteristic function of the positive reals. So the proximal operator to this prior would be our usual ReLU operator. And then another choice that people frequently do is to, for example, choose the total variation functional, which penalizes the gradient in L1 norm. So it basically promotes the sparsity of the gradients in the image, or, for example, promoting the sparsity in some other basis. And the commonly chosen basis here will be something that will be sort of a wavelets, but probably where we would prefer to have a frame, so over-determined basis, and because they will essentially align better with the particular features of our image, and then from those we'll be promoting sparse solutions that pick and choose exactly those the best aligned elements of the frame. So this would be the kind of typical choice of those regularization functionals. And let's have a look briefly at a kind of very simple abstraction of the problem I'm talking at, and how these choices impact the reconstruction. So if I think of my, I should have said that the optical contrast of the photoacoustic image of the photoacoustic tomography correlates with absorption of absorption coefficient of the tissue, and this depends on this correlates with essentially hemoglobin. So it also can differentiate between the oxygenated hemoglobin and the non-oxygenated hemoglobin. This is also the same mechanism that make those infrared sensors for the blood oxygen work that you can clip on your finger. So basically, we get this sort of information. So the photoacoustic images very often show some sort of vasculature. So this is the simplest model of the vasculature with pipes going through the tissue, and then we have our sensor sitting on top of the domain where we are going to measure the data, and we have vessels going through. with this phantom, we can just cut through it and look at the cross section. This will be giving us a good information about how well we are doing across, because it is essentially, it is essentially the same going that way. So the cross section, of course, looks like that. And now, if we take the full data as full data, meaning I have measured the time, the pressure over time at this sensor here, at all sensors locations, so the sufficiently resolved grid for the reconstruction inside. However, this is where my sensor is finite, so it ends here basically, and this is what I get if I back project the data basically. So what I can see here is that I can see those very specific artifacts, and these artifacts are coming from the boundaries of the sensors, and they are well understood in tomography. They are called there's microlocal characterization. So they essentially correspond to the circles, concentric circles that are tangent to those cross sections of those cylinders, and these are centered at the corners of the sensor. So these artifacts are artifacts corresponding to resulting from the limited view that I have because of the limited extent of my sensor. So now, if I, in addition to this, in addition to restricting the size of the sensor, which I have to do for practical reasons, I also want to be faster, so I want to subsample the sensor. So the photoacoustic data is essentially sequentially recorded. So for every point on the detector, you essentially need to repeat the process and record the pressure over time. So you can do it, to a certain extent in parallel, like I mentioned, multiplex through multiple beams. But this is still, I think that's the best sensors my colleagues produced had 64 beams that they can record at the same time. So it is still a process that this has to be repeated many times. So of course we are interested in limiting the number of those repetitions. So if I subsample the data in such a simple way, so this limited view artifacts are going to be scrambled somewhat through the randomness, as you would expect. However, they are kind of interfering with the visual perception, of course, of the image. So this is again back projected subsample data here. So now, if I pose that problem in a variational formulation and I iterate, so I run a couple of steps also of this proximal gradient algorithm, then, for example, for the full data, I can get rid of those limited view artifacts almost entirely. For the subsample data, it looks also pretty good. There's not perfect. So if I choose the regularizer smartly, in this case the total variation is essentially made for that image, so that I can see they get almost perfect reconstruction. Okay, so that is for this very simple example. So if I now go to a more to data that we collect in the lab, so what we are looking at here is again is a photoacoustic image that we time reversed the full data, and we are looking at something that is called maximum intensity projection. We correspond to I'm looking through the sensor perpendicular along the lines perpendicular to the sensor, essentially in the volume, and I'm picking the maximum intensity pixel along those lines, and I'm presenting that as my image. So this is essentially a 3D data set, but because of the relatively high transparency of this type of vasculature images, we can do this maximal intensity projection. So this is our gold standard, essentially. This is data collected in the lab, so we haven't biopsied that sample. So the reconstruction from the full data is the best what we can essentially do. And if we drop to 25% of the, so we did some subsampling, you can see that the deterioration from this analytical time reversal method, there's a lot of more noise and those vasculature becomes fragmented. So now we can try the total variation that did so well on this tube model. And now we can see that, well, it doesn't cope quite so well with this more realistic data set. So first of all, essentially there is no Goldilocks parameter value. So with relatively small difference in the regularization parameter, we go from things that get erased. So this kind of choice of regularization parameter erases certain parts from the image, or we have still too much noise. So we can for this particular problem we can work with curvelets, and this will provide us for this problem with a very good quality of the reconstruction. But it's not for every, I will be quite honest, this is not for every vasculature image. Okay, so this one was working quite reasonably good with curvelet. Not everyone will be working quite so well. It will in general work, at least as good as total variation or better, but there are some limitations to that approach. We know these functions are kind of optimal for edges along smooth curves, so that's not exactly what is happening in this sort of images. So because of these limitations of this constructed analytical priors, like the total variation or the curvelet, when the machine learning really came through, people started to consider the question if we can use sort of the information that we have in available data sets to learn the regularization. So it's quite natural idea. Instead of telling it to have the smooth edges along the C2 curves, we are telling it to look like a bag of other images and the data sets and the corresponding data that we have shown to the algorithm a priori. And so in a most general way, one can think of inverse procedure in inverse problems as constructing some sort of pseudo-inverse. And this pseudo-inverse is just a map from the data to the hopefully true image. And now in this framework, we want to introduce some parameterization into this pseudo-inverse that we can train the parameters on some provided examples, so that we can achieve our goal of mapping to the true image. And people have done that in many different ways. And this is for sure not exhaustive, and this is where the personal perspective will do a lot of heavy lifting. But let me mention just a few. So the most natural, I think, way of thinking about this, and probably the most theoretically sound, is to think of the regularization functional as learning the regularization functional, because this captures the information about the images. So we ideally would like to parameterize the regularizer inside of that for example, variational formulation, and train it. So, however, regularization functional comes with some strings attached, and to be able to still maintain the regularization theory, so that it puts some restrictions on how you would express this regularizer. So, for example, the classical standard neural network would not fulfill those assumptions, being a non-convex function. So there are variants that are input convex, but these have proven to be limiting. So there's an interesting strand of work going on about weakly convex regularizers, which fits in between two things and provides potentially some avenue for interesting results. So the other option is to think of this pseudo-inverse as a composition operator of kind of some sort of simple analytical inversion and a post-processing operator that we train to essentially remove artifacts. So another option is to parameterize the proximal operator in this unrolled iterative solver. So I take this proximal gradient and unroll a couple of the iterations, and I parameterize the proximal operator. I could have based my iteration on any other scheme. It could be a Neumann type of a scheme. It could be a fixed point iteration and parameterize the operators that appear in those. So there is a lot of work. It has been a lot of work in that direction. Something that you can do for limited angle problems, which I would like to spend some time with, is called null space learning, on learning the invisible. So the benefit of this approach is that, yeah, essentially I should get the performance on par with the unrolled methods that can capitalize from repeated operation, repeated application of the forward problem, and at the cost of the post-processing, essentially, by the virtue of being able to separating the visible part of the image from the invisible part of the image. And some other stuff that I should mention is also GAN-based approaches for in particular for artifact removal, and approaches in which people have just went for it all and just parameterize the pseudo-inverse map without necessarily trying to reuse any of the known forward operator mathematics. So just a few more words about the blue ones. So first, the post-processing. So as I mentioned already, it can be a composition of some analytical inversion with a neural network. And the idea is that this neural network should remove artifacts. And for that, this neural network will need to be a bit more elaborate. So usually people use something like a UNet, so it's a multi-level convolutional network, frequently used in imaging. However, what is nice about this approach is that once you have used your approximate inverse, your adjoint, whichever way you decided to do the initial reconstruction, you are not using the forward operator anymore. So you have some sort of back projected data, and then you are just working on that resulting image. So it means that you will not have to use the forward operator or the adjoint operator anymore in the training. So this is a great benefit. Okay, so the unrolled based approach, so where I unroll I can unroll essentially any method, and then it can be a convex optimization method with based on ADMM, for example, with implicit layers inside, or it can be this simplest proximal gradient algorithm, or it can be something that is not the convex method, like Neumann iteration type of idea. Here I just parameterize this application of this proximal operator, and I could insist on parameterizing the proximal operator, in which case, I should be paying attention to weight sharing between the iterations. I can just unroll so many steps and be completely free and think of this as a sort of a template of obtaining parameterization of the pseudo-inverse. And in each kind of iteration of my method, I essentially apply my neural network to. So well, here I perform a gradient step, but if you have a neural network, you can just provide it with two inputs and let it combine them. So for example, we'll take care of the step size for you as well. So this is sort of one iteration of unrolled method, and the hope here is that we can have far fewer of those iterations that we would have to do if we were iterating a convex optimization method. So in this situation, the network is usually quite a simple one. So something like standard feed-forward network would be usually used. And what you have to do is that at each iteration of a training, when you go through the training set, you have to, every time you touch a data, you have to apply the forward and the adjoint operator to it, because for the L2 square penalty, the gradient involves both those operators. So this is, of course, incredibly computationally expensive. So in order to be able to do it on 3D data, you probably have to cut some corners. So if you were to train it, if you were to train it for k iterations, then you would have to minimize this functional here, and this involves, as I mentioned, evaluating this this forward and the adjoint operator on the whole training set and every epoch again and again. So what you can do instead, you could do such a so-called greedy training. So basically, we are training one layer, and when we are done with that layer, we are training the next layer. This allows us to evaluate the forward and the adjoint operator on the training set exactly as many times as I have layers. So I just need to do it once per layer. This also allows us to grow the layers, so we can kind of decide how many layers we have. And we had good experience with this training. So this is what we used for our 3D photoacoustic unrolled method. And let me show you a few results. So if I do this first for the phantom, so we had to find some sort of data to train. Photoacoustic lab-based data sets are rather small, so we had to find some sort of synthetic data set to train it on. And this is a segmented lung vessels image, so volume-based data, and it will be one of the maximum intensity projections through one of those data samples. So if we now take the photoacoustic transform, so if we simulate the photoacoustic data and then back project that, this is sort of the image that we are starting with. So you can see that the photoacoustic images are already showing quite a lot in already in this initial stage. So that's even the simple inversion shows something. So this is what we are starting with. The question is how much we can improve that. And you can't see anything on the images on the top. However, the difference images show that definitely using the unrolled method, with in this case it was 5 iterations of the unrolled method, trained with this greedy fashion, so that we trained each layer until we were happy with it, and then we moved to the next layer. Versus the reconstruction that are obtained with simple post-processing with the UNet. So you can see that the unrolling pays off, in a sense that the difference images are much better, especially in the central region. So of course, the further out we are, the more limited data we have. So okay, so now if we apply that to a photoacoustic dataset, so we have trained on those synthetic images, and we did some transfer training on 20 photoacoustic datasets from the lab that were sort of looking like this image here. That's all volumetric data with the maximum intensity projections. And sorry. So this is the sort of result that we would get from total variation iteration. So 20 iterations of total variation. Of course, it means that we had to apply the forward operator and the adjoint operator 20 times. In that case, it is solution of the time domain wave equation. It's quite time consuming. And it took about 10 minutes. And this is the sort of the image we get. Total variation, we have seen before, has its limitations for this sort of images. And when we use this 5 iterations of the unrolled method after this transfer training from the synthetic data. So this is the sort of the result that we are getting. So it's not perfect either, but it's in terms of quantitative metrics. It beats the total variation. It took only 5 iterations, so it took only 2.5 minutes. Okay, so this is the sort of reconstruction we are getting. So we kind of were still a little bit upset about the time for the application of the forward operator. So we tried to speed it up using some approximation. And we used a Fourier methods. And I will say something more in a moment about the Fourier methods. But at that moment, here just very simple way we used a Fourier method, which would provide an approximative forward operator, and also approximated inverse operator, of course. And this is the result that we get. So the slightly different data sample, but so this is the fully sampled reference, and this is what you would get from the total variation, 20 iterations for that image. And this is what you get using this approximated Fourier forward operator inside of the unrolled learned proximal gradient. Again, 5 iterations. We just replaced the forward operator, and this took only 20 seconds. So it is much faster, and the quality is kind of quite reasonable. So it's an old question how why you iterate, how well you have to really actually evaluate your forward operator, especially in the initial stages of your iteration. So this is definitely a justified question, especially with the gain that you are seeing here. So this essentially it drops an order of domain size, if you wish. Okay, so let me now tell you a little bit about this Fourier approximation. So this result motivated us to look at this a little bit closer, and so essentially it is a Fourier solution to the PDE. So we assume, as we usually do in photoacoustic, constant speed of sound, and we are this derivation here specific to the half space sensor geometry, and we assume the symmetry across the half space. So in my case, I usually assume even symmetry, and otherwise, because of this Fourier method, we are endowing this with the periodic boundary conditions essentially. And so we then have a Fourier solution to this wave equation. Oh, I am going too slow. We have Fourier solution to this equation, and we can plug that into the photoacoustic data. So we can plug that into the wave equation and evaluate it at the time and at the sensors over time, and we can get the Fourier domain version of that to give us a relation between the initial pressure and the solution of the wave equation at the detector. So basically, I have this relation between my Fourier transform of my image and Fourier transform of my data. So this is what I end up with. And this formula is quite old. It is called back projection formula for photoacoustic, and but not in that form, but just if the form where you want to recover P0 from the data, basically. Okay, so you just get this fraction on its head on the other side, and you have to change the variables so that it makes sense for your spatial variables, for the image domain variables. But this is essentially the same formula. So now we want to use this formula as a forward operator. So we now get this fraction in that form here, and then we can see that the denominator can blow up. And this is why you can't use this formula per se as a forward operator, as well as the periodic boundary conditions that are causing certain issues. What we did in that paper when we used that, we just regularized that. Okay, we just restricted this fraction, and that's it. And so now when we review the geometry of this formula, we observe that this is nothing else than just the change of coordinate between the Fourier domain of the image space and the Fourier domain of the data space, and this is the change of coordinates, and so basically there is the sensor coordinate is the common one, and the change of the coordinates only happens between the frequency corresponding to time and frequency corresponding to the direction that's perpendicular to the wave propagation. And this, I can get this change of coordinates from the dispersion relation of my wave equation. And this means that so this is visualized here as that I have my data domain frequency plane, and I can see how this isospatial frequency contours map like that on my data, basically. So this is the change of coordinates that I am getting, and this change of coordinates is also visible in that I can see each singularity that arrives at my detector. I can see the singularity in my data. So if I have a point source and this propagates, there is a pulse and spherical wave propagates from that point source, and then through the given times it arrives at the detector in different points under the different angles theta. It will, first of all, it will leave this hyperbolic trace in my data space, but also I can see that singularity, so that's direction of this wavefront. I can see the direction, and I can find that in my data. So there's a one-to-one map between those two, and this has the implication that if the directions are getting mapped to directions. So if I have a sensor, and many physical sensors will have this property, that not all the directions of the wave are recorded. So the sensitivity varies with the angle of impingement at the sensor. So for example, the simplest example, we could think that if the wave impinges under the certain angle that is larger than, let's say, pi 4, like 45 degrees or 60 degrees, that this is not being recorded anymore. So the very steep angles here. So here we see about 45 degrees. Yeah, but if it goes steeper, then it's not going to be recorded. Then my sensor is essentially blind to those directions. So it means they are not in my data. So it means that I have a restriction of what I'm recording in terms of my image, and this maps to the restriction to of course what I recorded in my data. And this is visualized by those cutoff asymptotas here. They are kind of squashed, and they further restrict the Fourier plane that I am recording. The upshot of that is that this part beyond this red asymptota was exactly the part that caused my blow up in my Fourier formula. So actually it means that I can use the Fourier forward operator modulo the periodic boundary conditions. I can use that as a forward operator for the photoacoustic image, for the photoacoustic tomography under the restriction of the visibility angles. So I can formally derive the whole suite of those forward, inverse, and adjoint operators on the Fourier domain. And I can implement them as well. And if I can find a basis for my image that aligns with the visibility angles that I have, so with the aligns with the with the cutoff of my Fourier plane, then I can exactly partition the image into what I can reconstruct and what I cannot see. And a basis that is well suited for reconstructing such a directionally resolved resolved interfaces is for example curvelets. And if I construct my curvelet basis so that I align the wedge exactly with the cutoff of my sensor, then I can have an exact resolution of the visible part of my image and the invisible part of my image. And what this will allow me to do is that I can reconstruct the visible part using standard convex optimization method, and the invisible part will not interfere with it at all. Okay, so this is for this we kind of have this variant of the curvelet transform that we call wedge restriction, and this is essentially a projection operator applied to the standard curvelet transform. And the one more thing we have to look at is the coarse scale, because the classical curvelet at the coarse scale would have isotropic wavelet coefficient, so they will be non-directional. But we can induce the directionality just by simply extending this bow tie filter to the coarse scale, where the directionality we just essentially inherit from the atom of each of the pixels. We inherit the directionality. Okay, so this is the modification that we are going to introduce into this curvelet. And with this basis, we sort of the basis decomposes the image into the visible and invisible part, as we can see on this example here. So the standard curvelet transform is a numerical isometry. So we have a left inverse. So when we apply the curvelet transform and this its pseudo inverse, we will obtain the image back. As you see, we can have an error of machine precision essentially. If we apply the classical curvelet with the wedge restriction, but with isotropic coarse scale, this is what we get. So basically, we are only picking the visible part from the higher frequencies and maintaining the whole coarse scale. And if we extend the directionality to the coarse scale, this is the total projection that we get. And the last one is the one that is corresponding to these measurements that we are collecting with the directional with the limited angle data. So we are going to use this this last variant, and we are going to reconstruct the visible part using a convex optimization problem, and we are going to learn the invisible part. And why would you like to do it like that? So first of all, you have a separation of blame, so you can separate the measured data influences purely the convex reconstruction, and there is no influence of any learning into this. And then we have the learn part that we learn really on how the image should look like, and then we put that into the invisible part of the image that we have no measurements about. And on the other hand, there's also the issue that because we have with this convex optimization problem, we basically extracted every little bit from the data we could, and then there is no more reason for us to do anything with the forward operator for the learning problem. Yeah, so we don't have to include the forward operator into the training for the invisible part, because we will have no benefit of that. So it decouples, it offers us this kind of cheaper way of doing things. So the last part is how do we construct a network for learning the invisible. So if we were to take each individual curvelet, we would have to have a lot of functions of this sort of looking like this in the top row to learn, so that doesn't look very efficient. So if we collect all the curvelet coefficients, or the visible and invisible coefficients at each scale, this is the sort of pictures we get, and we just have one per scale for visible and one per scale for invisible, and we call it corona coefficients, just from the filter bank, basically, that does the filtering for the scales. And this is what we use in our network construction. So we just have modified a unit in such a way that we first of all the composition operator. So instead of being downscaling standard network downscaling operators, all these operators are the compositions, the curvelet decompositions essentially, but they are just the filter bank for the scales, because we are bunching the curvelet, the bunching the coefficients for each scale together. So they're essentially the filters for the annuli that correspond to the coronas. And so this, the filters for the multi-scale analysis, I should say. And so this propagates down the unit, and going back, this is how you put together the filtered parts in the same way as you would have done it for curvelet, for curvelets. But there's no, there's no individual curvelets, so that doesn't add extra computational effort for computing individual curvelets, because individual curvelets require you to apply the wedges, so it would complicate things and would make it much more expensive. So that's not the part, it's just the big filters. And we have input, we input these corona coefficients, the visible ones and the invisible ones, and then the invisible ones are the ones that are learned. So basically they have some sort of random initialization, and they expect it to be filled in at the other end of the network. And there is sort of this construction has this same space scale properties as is matched to the curvelet decomposition and to the image, and is matched. There is no cross talk basically between the scales, and so that's why you can input those corona coefficients at different scales, just at particular level of the unit. There is no point for them to be inputted in the top, because it would just be passed down. So you can have a variance of that, including residual connection, to kind of to allow for your coefficients to be not perfect. So the visible coefficients to be not perfect. And then essentially this is the sort of the results that we get. So when we have this reference image, and this is the L1 reconstruction. So I think there was a visibility probably of 45 degrees. That's how it looks like. And so 45 degrees angle and all beyond that were not recorded. So you lose a lot of those singularities that are the angle steeper than 45 to the detector. So this is the reconstruction that you can get from the convex optimization. It cannot compensate for the invisible part, so it just reconstructs the visible part. Okay, so this is the TV reconstruction, and the TV reconstruction suffers at places here with the contrast, so the two highlighted with sort of varying contrast in comparison to here. And then in general, TV, will do a relatively good job on the background, so you are more concerned about kind of smearing the thinner parts of the vessel. So if you compare this to just units, so you just input the visible part of the image, and you expect it to fill in the invisible part of the image in the same image, this is the sort of reconstruction that you get. So it struggles to remove the artifacts, for example, from the background. If you construct a reference unit that is a bit smarter than the standard unit, it uses our corona coefficients, but it doesn't use the corona decompositions and so on. So then you can already, with the idea of using those corona visible and invisible coefficients, you can get already quite far. So this is the result that we get from that, but the background is not, it's not perfect. So, and we can see that this kind of gets all gets improved when you go to the full corona net that we have discussed. So when we also use the proper multi-scale decomposition for the network. So you can see this sort of in the quantitative matrix as well. So the last three are the reference units. So the simple reference unit, when we just ask the unit to fill in the invisible part. So that's kind of not doing quite so well as the L1 and TV methods also are not doing great in terms of those metrics. Where you really see the jump is where you start to use the corona coefficients, and then in this case the MS is actually slightly better for the reference unit with the corona coefficients, but for the other metrics they're still better when you have the full corona net architecture. This kind of the message is mainly that just properly decomposing the image in a way does a lot of weightlifting here. And I probably should finish. So this is a clean cut. I can just stop here. I probably should. Yes. Hello.